Hello everybody. We will start quantification of basic events for repairable components. In fact, I have discussed little bit of this in my past earlier lectures, and primarily we have discussed the basic event quantification for non-repairable system, and there we have discussed about your reliability, failure distribution, failure density, then failure rate, and then I have discussed similar parameters for repair process under repairable systems. Today we will extend this and we will see some of the other important parameters for repairable system or repairable component in this case. So, we will discuss today what is availability, what is unavailability, what is conditional failure and repair rates, and unconditional failure and repair rates. And then we will give one example, and we will from that example we will see that how those parameters can be computed. And most of the materials for today's lecture has been taken from this book, Probabilistic Risk Assessment and Management for Engineer and Scientist, written by Kumamoto and Henley 2000. So, let me recollect what we have discussed so far related to repairable system or a repairable component. So, you know that we have assumed two states. One is either the component is working or the component is at failed state. So, if the component is working, we say it is normal state, and if it is component is in failed condition, we say it is failed state. So, when a component is at normal state, it may continue with the normal state, or it can go to the failed state. That is, going from normal state to failed state is, we say that is the transition from normal to failed state, and then the failure process, repair process start, and after some time the repair is completed, and again the component will come back to the failure for the normal state. So, it is similar to like this, a component over time and the component either at the failed state or at the normal state. At time t equal to 0, it instantly jump to normal state, and then it start working and continue working, and maybe at up to time t it is working condition, and then here it and with in between t plus delta or t plus delta t dt time, this within this time it will undergo a failure, then it will shift to this is the failure state, and maybe failure process starts. So, that is what is the in terms of that graphical representation given here, and this is what is happening over time. So, I have told you earlier that the failure process time, we have time to failure and then time to repair. So, both the things will be combined here, and that is why this is a combined process where that failure to repair and again repair to failure, both the things will be combined here. And one more example, let us see that a better example where suppose there are 10 identical components put under test, and we are observing over time that what is happening with the component, whether it is under normal state or at failed state. For example, if you consider component 1 and the time 7 units, means t equal to 7 here. So, then the component 1 is at the failed state, because here the failure state it is failed. So, if you consider component 10 you see that component 10 is under normal state. So, what happened to component 1, a component 1, once it failed, then repair starts, and I think at around 7, okay, it is under fail state and it failed at around 6 point some units, and it is repaired again at 7.1 units, and then it jumps to the normal state, and again it continue working at the normal state, and finally what happened again at time unit 8.1, I think 8.1, it failed and the failure, that fail state continues. So, as it is a repairable system, what happens, so long it is working, so it is normal, and when it fails, it goes to the goes to the failure state and repair process starts from there. So, that is what is the concept. Now, as all the components are identical in nature, so we can use this phenomena or this experimental data to compute that what we are the same survival function, that is reliability function, this failure distribution, failure density and failure rate using the formula already given to you. Okay. Now, you see how you will use this information what is shown in the graph, and you ultimately come to time to repair time and failure time of each of the different components, and from there how to find out the time to failure, and also you can find out time to repair. For example, although there are 10 components, but because of the combined process in nature, failure to repair and repair to failure, what happened actually many of the components are going through failure as well as repair process, and again after repair it is working as again at the normal state. So, number of observations, that the failure observations is therefore not 10, it is more than 10. So, for component 1, you see that component 1 we started with 0, and then failure repair at the time when it is time t equal to 0, we are assuming that it is instantly repaired to normal state. So, the repair time is 0, and then you see that it worked up to this time, means this time which is equivalent to, which is basically 6.4 unit time. So, that means the component 1 failure time to failure is 6.4. But what happened that we have considered 10 time units, that in between that 6.4 unit time to 7.1 unit time it was under fail state, but at the 7.1 unit time this component is again at the normal state because repair process completed. So, what and that is what is written here, it failed at 6.4 unit time, and again it is repaired at 7.1 unit time. So, the difference actually is this one, this is the time to repair. Now, as the component 1 is again operational or at normal state at time unit 7.1. So, we are considering the repair is as good as new. So, then again we are looking for that how long it basically works. It works from 7.1 to 8.1 units. So, 7.1 it repair completed, it started working, and 8.1 unit it again failed and then remain in the fail state. So, that is why what happened for component 1, we got 2 time to failure data, one is 6.4 and another is 1. In the same manner or similarly, we observe the failure of component 2, component 3, component 4 like this up to component 10, and these are documented here. So, component 1 within this 10 unit of time undergoes two failures, one at 6.4 unit of time, another one is at failure time 7 point failure mean 8.1 unit of time. So, 6.4 and 8.1 unit of time, two failures. Component 2 first failure at 4.1, you see that it fails here 4.1. It repair in this time, that is 6.3, but again it undergoes failure at 6.6. So, 4.1 and 6.6. So, 2 times it fails, it repaired and again it fails. So, accordingly you got 2 time to failure data for component 2. In the same manner, component 3 1 time unit, component 4 1 time to failure, component 5 2 time to failures, component 6 2 time to failures, 7 1 time failure, and 8 1 observation, similarly 9 another 2 observation for time to failure, and 10 1 observation for time to failure. Essentially, if we count that how many then observations we obtain 15 observations. So, that is why when all those observations we have counted that as if there are 15 units which are put under test. This is possible because of two things. We say that at time 0 it is instantly repaired and it is at the normal, and with the feature that or property that it is as good as new, and again when we repair at after certain time, maybe at time t equal to t naught or t equal to t 1, at that time if the repair is completed, we are saying that the repair is also such that it is as good as new. So, that means whenever repair takes place, the new component has been put. This is the similar, analogously we can tell like this, and as a result this experiment is basically analogously an experiment where 15 identical items are put under test. So, as a result at t equal to 0 there are 15 units. So, then what will be the reliability? That formula you know, that there is basically all 15 surviving divided by number put in the test. So, 1, and in this manner that how many failed within 0 to 1 unit, the 2 units fail. So, like this 13 surviving, 10 surviving, this much you have done already. As a result, you are in a position to compute all RT, the reliability or survival function, and FT is 1 minus RT. So, that is the failure function that you can compute. Once you know RT, you can compute the FT. Similarly, small ft, which is basically density function. So, that you can compute how basically that the within the time interval what is the number fails, and divided by total number put under test at t equal to 0 into divided by the time units. So, that means this minus this divided by this into the difference in time units. So, that formula I have already given to you. So, you know this. So, you can find out the FT, and at the same time RT also you can calculate what is basically RT is basically failure rate or instantaneous failure rate, which is small ft density by the survival. Means it is something like this, that what is the probability that the component will fail at within t and t plus delta t, given that it has survived up to time t. So, these things you have already computed, and but we have given you the example, and now with reference to this, where although we have 10 component under test, but because of the combined process, that means it is normal, then it is under failure process, then once it fail it goes under repair process, then once it repair again it will go under the failure process. So, that in that manner what happened, every component is undergoing through failure and repair, and as a result in this case from this experiment every component is giving us one or more repair time or failure time. So, now we have considered only the time to failure, and accordingly we have computed these parameters. So, similarly you can find out the time to repair and the repair related parameters by repair distribution, repair rate you can compute. Okay, and I hope that you will be able to do it, and I request all of you to practice this. The failure point of view I have discussed. From the repair point of view, find out the time to repair from this figure, and at the same time you find out the failure repair distribution, repair rate, repair density, all those things you please find out. But interestingly, what will happen under such combined process, that this reliability or the density or the failure rate, they are not the only parameters that describe the properties of the component from failure and repair process point of view. In fact, what if we talk about the reliability, and then by definition of reliability, suppose let us talk about the component 1. Okay, so at 8th unit of time, suppose when your t equal to 8, that time if you see the component's condition at time t equal, it is basically normal. Okay. Now, if I want to know what is the reliability of this component t equal to at t equal to 8, so if we ignore the failure process here, so what will happen ultimately? Ultimately, you will basically yield a wrong results, because reliability will not consider in between the failure states. Reliability means what is the probability that the component or the system will work within this mission time, here t equal to 8, without failure basically. But what happened here, the component failed and again repaired and it is working. So, that means we require some other measures which basically will be maybe a better measure from the repairable units or component or systems behavior point of view. So, those measures will be of discussion, or I can say the focus or the focal points for today's lecture. So, let us see what are those parameters or the distributions which ultimately describe the combined process more meaningfully. So, we will introduce now to you two important concepts. One is availability, another one is unavailability. Now, let me draw a figure here. Suppose I am interested for a particular component, let it be a valve, and then what happened? It is when it is purchased, let t equal to 0, a new one is purchased. So, we are assuming that it is basically repaired to new normal state, and then it undergoes operation, and at time t equal, this is t. So, at this time period it is t plus delta t is failed. Now, if I ask it failed, and again suppose it is in failed condition, then what happened? At this point in time it is repaired, and then it is again under normal condition. Let it be like this. So, so what happened? Suppose at any point in on time, for example, at this point. So, is the component available? You will say yes. If I say whether it is available here, suppose t plus delta t exactly, you will say no. Again it is available at, suppose this is the t equal to, let it be t1 plus delta t, and let t equal to t2. Is it available? Yes. Because of the repairable nature, the component will be available or unavailable at certain point in time. That is very important, and you must know that for repairable system, whether the component for repairable component, whether the component for repairable system, whether the system is available or unavailable at a particular point in time, and that definition is also very important for safety studies. So, that is why now we formally define what is availability. Availability is the probability that the component is normal at time t, given that it was as good as new at time 0. So, at time t equal to 0, it was new, and now we are considering a time instant, like let t equal to t here, whether it is, what is the probability that it will be available, it is available here. If I say no, t equal to this, what is the probability that it is available here. So, you keep in mind this one. Availability means at a particular point on time, we are interested to know whether the component or the system is in normal state or not. Then unavailability means just the opposite, that at a particular point in time, whether the component is failed state or not, component is in failed state or not. But for both the cases, please remember that the component was as good as new when it was first manufactured or first started operation. That means, at the beginning when t equal to 0, it is as good as new. That is what is given here. Probability that the component is normal at time t, given that it was as good as new at time t equal to 0. Then what is unavailability? You see, the probability that the component is in the failed state at time t, given that it was as good as new at time 0. Okay. So, that is why what happened, a component will be at a particular point on time, it will be either available or not available, two states. As a result, the probability of availability or unavailability, so that means if the sum of probability of availability and sum of probability of unavailability will be 1, that is written here. So, if you recall my previous lecture, so in one lecture I say that reliability plus failure, that is cumulative distribution, that also 1 we said. Now, we are saying availability and unavailability, the probability is also 1. But there is fundamental difference between, because reliability and availability as well as unavailability and failure probability, fundamental difference is there. So, I told you earlier, I started describing what is the difference. When you talk about reliability, reliability requires the continuation of the normal state over the interval 0 to t. Okay. So, if I say I want to know the reliability here at t equal to t2, see what happened for this component has failed here. So, it violates the assumption that it is continua or working within this. So, but for availability it is not. So, a component contributes to the availability, but do not contribute to the reliability if the component failed within t unit of time. Okay. So, as a result, a component availability, probability of a component's availability will be more than the probability of the components reliability, or other sense I can say the probability of component having at normal state and probability of component fails with the less than that time, they talks about two things, one is availability, the first one, and second one is the reliability. And because of the requirement of continual that normal state condition, this relationship holds for any component or a system also. That means availability is more than or equal to reliability. It is obvious, because that once it failed, it will not contribute to reliability, but once it failed, it is repaired and then again it is under normal condition, that contribution goes to availability. So, fundamentally this is correct. But if the component is not repairable, means it is a non-repairable component, then again you will not get it under normal state. So, at this situation both will be same, availability and reliability are same. Okay. I hope you understand this. In the same manner, analogously we can say this, that unavailability is less than that cumulative failure probability, and and this one will be equal when component is non-repairable. Okay. I hope that you understand the two concepts, one is availability, another one is unavailability, the relation between availability and unavailability, the relation or the inequality from availability and reliability point of view, and unavailability and failure probability point of view, that relation that you understood. And for non-repairable system, availability equals to reliability and unavailability equals to failure probability. So, that is why the reliability and failure probability are sufficient enough to explain availability and unavailability. So, you do not require availability and unavailability separately there, but when it is a combined process, reliability and failure probability will not give you the complete picture unless availability and unavailability is also taken into consideration. This is your first concept. Okay. Then the second another important one is that, very important one, that failure intensity. Now, failure intensity can be conditional, can be unconditional. Okay. So, both case we are talking about failure intensity. So, what is the failure intensity? So, failure intensity is also the probability that a component fails per unit time, at time t. Here you see the component fails per unit time at time t. Now go to the availability again. Let us go back to availability. Probability that component is normal at time t, but what we are saying under conditional, that we are talking that fails per unit time, per unit failure, but when? Given that it was as good as new when at time t equal to 0 and normal at time t. Okay. So, if you draw, suppose you draw the figure again, or suppose this is the figure. So, this is t. What we are saying, suppose t times elapse, we are having basically a unit time, let us consider t plus small unit time. So, usually we say t plus delta t. So, we are interested to know that what is the probability that the component will fail per unit time here within small, if we make this time units very small, but given that it was as good as new when t equal to 0 plus it is failed at time t equal, it is, sorry, I just taken a 1 minute please. Yes. So, time t equal to 0 and normal at time t equal to t. So, that means suppose this normal time t equal to t. So, similarly we can do same thing for the repairable case or repair process also. That means the conditional repair intensity, unconditional repair intensity. So, first we are describing the conditional failure intensity and unconditional failure intensity. So, what are the condition here? Condition imposed is that the component is normal at time t. What is the probability that the component fails per unit time at time t, given that at time t equal to 0 it is as good as new and it is normal at time t. Now, if I go to the unconditional part here, what is the difference? Probability that the component fails per unit time at time t, given that it is as good as new at time t equal to 0, no condition imposed on the component at time t. That is why the unconditional word is used. In fact, for all the component cases at time t equal to 0, we are considering that it is a new component. Okay. Now, this is denoted by lambda t. Then, what is lambda t dt? Lambda t dt talks about that a probability that a component fails during this small interval. Within this t and t plus delta t, the component will fail. What is the probability that component will fail within this small unit of time? When we are talking, and when you make it the small unit at unit time, then it is basically lambda t. That means, when I make this delta t equal to 1, it is nothing but lambda t. So, what are the condition imposed? Condition imposed is when at time t equal to 0, it is new. Another condition imposed is it is normal at time t equal to t. Okay. Now, now come to the another important quantity, that is RT and DT. So, you know what is RT? I explained earlier, RT is failure rate. Then what is RT DT? Failure rate times multiplying the small time unit. This represents that the component fails during t plus delta t, that component was repaired at time t equal to 0 and has been normal to time t. So, okay, at time t equal to 0, it is repaired to in such a manner that it is as good as new, but it has been normal to time t. But in case of lambda t dt, you are not saying it has been. When once it repaired, after repair till the next that time we are considering, that is normal. It is not like this. In the first case, at that particular time instant, it is normal. That is why we are writing it is normal at time t, but here you are writing has been normal to time t. So, as a result, both are talking about probability that the component will fail within the small interval t plus delta t, but in the first case lambda t delta t, we are talking about that this probability that the component is as good as new at time equal to 0, that is true for the both the cases, but it is normal at time t at normal state. But in the second case, it has been normal. So, that in between there is no failure. So, as a result what happened, these two lambda t and R t, they are not equal, and if you consider that it is a non-repairable system, then it is equal. General case, repairable case, it is not true. So, analogously you can create this W t dt. So, what happened? Only the condition at time t that is relaxed here in the unconditional case. So, as a result, what is W t dt? W t dt is the component fails in the small interval t and t plus delta t, given that the component was new or as good as new at time t equal to 0, and the quantity W t dt represents the probability, that is what we already told you. And now what will happen for non-repairable component W t and F t, failure density and unconditional failure intensity, they basically equal. The crux of the matter, the difference here, apart from the definitions given here, the difference here is that lambda t, which is basically conditional failure intensity, it presumes a set of component as good as new at time 0 and normal at time t, whereas unconditional case this assumption is relaxed. Please keep in mind. Okay. So, what you have learned so far then? You have learned many things. Quickly, for today's presentation point of view, let me tell you that you know availability, you know unavailability, you also know their availability relation with reliability, unavailability with FT, and then what we have discussed lambda t conditional failure intensity, Wt unconditional failure intensity, then lambda t its relation with failure rate and unconditional intensity with the failure density. Apart from this, with the example we have seen that how the computation is possible, but that availability and unavailability, this intensity and unconditional intensity, that computation I will give you after 1 or 2 minutes. But before that, one more important concept you must know, that we are talking about that if once a component fails, it will be repaired and again it will work, and again it fails, it will be repaired, and repair process will bring the component to as good as new condition. So, that is why we are interested to know another quantity, which is expected number of failures. So, what is the expected number of failures in between t and t plus delta t, small time, given that the component is as good as new at time t equal to 0, then this is the formula. This is very simple one. So, it is basically sum of I times probability that I number of failures during this small interval of delta t time, and given that the component is as good as new at time t equal to 0. Now, if the delta t interval is so small that only one failure can take place, then this lead to this quantity. Small, you choose your time interval, like you are basically choosing the time interval. You make the time interval very small, delta t very small. In such a manner you make that within a very small time, only if failure occurs, only one failure possible, then I will be 1, and in that case this is W t expected, that is number of failures will be W t into d t, where W t is unconditional failure intensity and d t is the small time interval. Now, if you want to know within 2 time interval like t 1 and t 2, so then you do integration. Okay. Just what will happen if it is a non-repairable component? this what is the expected number of failures in between 0 to t, it will basically the failure probability, and it will become 1 if you consider a longer time, sufficiently long time, and the number of that means expected number of failures will be infinite if t is infinite for repairable system. So, I will not discuss this unconditional or conditional repair intensity. The discussion what we have made so far with reference to conditional and unconditional failure intensities, that is sufficient for you to understand this slide. I have given sufficient material in the slide, so that even if you do not understand many times, so you can go through and recollect what you have learned earlier. At the same time, you pause the video, again listen and understand. So, here only thing I want to tell you, when you are talking about conditional, when you are talking about conditional part, you see that failed at time t equal to 0. When you talk about unconditional part, such situation, such condition is relaxed. Okay. Otherwise, what happened? This mu t is the conditional repair intensity and m t is the repair rate. So, they will be same for non repairable system, and like expected number of failures, you also require to know expected number of repairs. So, that is what is V and dt, V t and t plus delta t. The expected number of repairs means within t small time interval how many component will be repaired when we consider that they were good, they were new at time t equal to 0. Okay. And analogously, you will within a time interval t 1 and t 2, this is the number repaired, and similarly this will be 0, that repair that number expected number of repair will be 0 for non repairable system, and expected number of repair will be infinite for repairable system is t is very large, t tends to infinite. And another interesting one is this. What is this QT? Unavailability, probability that the component is unavailable at time t equal to 0, when it is good unavailable at time t equal to t, when it is as good as new at time t equal to 0. This is the difference between expected number of failures and expected number of repairs. Okay. And in combined system, in case of non repairable case, you have seen that mean time to failure. And when we talk about the combined system and only repairable part we have considered, you have seen that mean time to repair. Now, the failure and repair both processes combined, so you are getting mean time between failures or mean time between repair. Okay. So, normal, fail, again normal, again fail, again normal, like this. So, now this is your normal time, this is fail time. So, now mean time between failures. So, this is my first failure, and then it is repaired, and then again it is second failure. So, what is the mean time between failures? So, that is why it contains both mean time to repair failure and mean time to repair. So, similarly, mean time between repairs also will be the same, mean time to failure plus mean time to repair. So, this is what is the final one. Okay. So, I just ask you to go through this book, Komamoto book, and you please see this example, similar example there, and the computation part, whatever definition I have given to you here, that is sufficient, and you will be able to compute availability, unavailability, unconditional failure intensities, expected number of failures, all those things. So, with reference to this is given, go through, practice it, write on the discussion forum and the books like this. Thank you very much.